Welcome to this video in which we will be talking about errors of numerical integration, so that by the end of this video you will be able to estimate the errors that you make when you use a Newton-Cotes integration technique. Now, errors, right? What was the definition of an error? The true error was the true solution minus my numerical solution. Now, the problem with this formula is that we need to know the true solution, and we typically don't know the true solution because we're using a numerical solution because we don't know the true solution. But can we say something about the error without knowing the true solution? And as an example, let's just look at the rectangle method. Okay, so I know that the true error is the true solution minus the numerical solution. And so the true solution would be the integral from a to b of f of x dx minus the numerical solution. And if I use the rectangle method, that would be minus f of a times b minus a. Okay, now I don't know what that integral really is, but let me use the Taylor series trick. Let me do a Taylor series expansion for f of x around x equal to a. So the function f of x is equal to f of a plus x minus a times f prime evaluated at some unknown location psi that I just know is somewhere between a and b. That's using Taylor's theorem. Right? And so let me use this definition and plug it into this integral. So the integral from a of b of f of x dx is equal to the integral of, well, f of a plus x minus a times f prime of evaluated at this unknown location psi dx. All right, so let me do this integration. I can definitely integrate this first term here. Right? The first term will give me f of a times b minus a, because f of a is just a constant value, so times b minus a. And then I have to integrate this second term here, and that one would be a half if I substitute in the integration bounds directly, so a half b minus a squared times this f prime at some unknown location psi. Okay, so that's my stand-in for the exact true solution. So then the error is this stand-in for my true solution. So let me just copy that value over here, this formula, minus my numerical approximation to the integral, which was done using the rectangle method. So minus f of a times b minus a. And so now what you see is that you have f of a times b minus a there, plus and minus. So those two will cancel. So my error will have the following form. It's a half b minus a squared times f prime at this unknown location psi. Now, let me just reiterate, we can't use this formula to calculate a numerical value for the error, because we don't know what psi is, and we don't really know what the derivative of this function would be anyway. But the equation tells us something of how the error behaves. It tells us that the error will be large if the derivative of f, so if f prime at this psi is large, and or the error will be large if b minus a is large, meaning the length over which the area over which I'm integrating, so the a minus b. When that is large, if b is far away from a, I will make a large error. Now, how can I address this? Well, I have to reduce this distance over which I'm integrating. And how did we do this? Well, we used a composite method, meaning we did this integration not over the entire integral at once, but we did it over subintervals, thereby reducing this effective integration bounds. So let's see what happens if I'm using a composite method. So I'm integrating over a subinterval, so not over the entire from a to b, but instead over a subinterval of size h. So the error that I'm making per subinterval is a half h squared times f prime evaluated somewhere within the subinterval, so let me call that location psi I. Okay. Now, the error for the entire integral is now the sum of the individual subinterval errors, because the integral over the entire from a to b is the sum of the individual subinterval integrals. So if it's the entire sum, then I have the sum over all subintervals, so I equal to 1 to n of e sub I. We substitute this in. It's the sum from I equal 1 to n over half h square f prime at these unknown locations psi I. We factor out the half h squared. And so now what I have is the sum of the derivatives evaluated somewhere within each subinterval. So let me define an average of these f prime values over the entire interval from a to b, and let me define this by this sum of the f prime at these subinterval locations. So the average then would be the sum of these f primes divided by, well, the number of terms that I summed up, so divided by n, the number of subintervals. Okay, so let me substitute this in. So the error is a half h squared times this sum, but if you look at this sum here, the sum can be now replaced by n times this average f prime. But I know how many subintervals do I have? Well, that depends on the subinterval size h, right? The smaller h, the more subintervals I have to go from a to b. And in fact, the subinterval size was simply b minus a divided by n, the number of subintervals. So that means that this n in my error formula is just b minus a divided by h. So let me substitute this in. So I have half h squared times the n, but that is b minus a times h, and then times this average of f prime. And now you see here that I have an h squared divided by an h. That leaves me just with one h. So the error would be b minus a over 2 times h times this unknown average value of f prime. And now the important thing is, right here, you see that the error is proportional to the size of the subinterval. It's proportional to h. So this is a first order method, right? If I reduce the spacing, the subinterval size, by a factor of 2, my error will go down by a factor of 2 as well. Now, we can do this analysis for each one of the integration methods. So, for example, the composite midpoint method has the following form of the error. It's proportional to h squared. So it's a second order method. The composite trapezoidal method has this form of the error, and there it's the average of the second derivative, right, over all the subintervals. But the important thing is that this is proportional to h squared. So again, this is a second order method, which means that if you reduce the spacing h by a factor of 2, your error will go down by a factor of 2 squared. So it would go down by a factor of 4. Now, the composite Simpsons 1/3 method turns out to be a fourth order method. It's proportional to h to the power 4. And then finally, the composite Simpsons 3/8 method has the following form of the error term. It is proportional to h to the power 4 as well. So this is a fourth order method as well. One additional comment on this. If we could somehow bound the average of these derivatives, right? We could bound the error. We would have an upper bound, right? We would have some plus minus bounds available for our integral. But it turns out that this is really difficult to do in practice, so it is typically not done. Thank you for watching.